Okay, off we go. So here's where we were last time. We were looking at this example. And again, this is an example. I'm going to show you 4 different solutions, 3 of which are actually good, 1 of which is the best, and 1 of which is actually a little bit of a problem. So anyway, here we go. I think we already talked about these 2 parameterizations. Can y'all remind me, did I talk through these parameterizations, I believe? I think so, yeah. Okay, yeah, good. Okay, so the big idea is, there's tools for your toolbox, different ways to parameterize the same curve. In fact, different ways to come up with the same parameterization for a given curve. Here, on the left, I sort of made a geometric interpretation of my parameter and then used that to infer the polar coordinate theta and then write down good old, polar coordinate formulas. That's one way to come at it. Totally different way to come at it is to realize that there is a reflection there that relates a parameterization I already know to a parameterization that I'm looking for. Right? And so different tools, but they lead you to the same parameterization, and you can take this parameterization arrived at by either argument and just plug and chug, right, with the usual formulas. Okay. All right, so here's the best way to do the problem, I think. And that is to say, look, it's the same curve. We've already computed this line integral to a t with one little microscopic, well, actually kind of significant, but just the one little sort of change, and that is that we're going the other direction, right? We've already computed the counterclockwise vector line integral. We just want to compute the clockwise, and so I'm going to argue by saying, look, you want me to compute the clockwise? You want me to compute going the opposite direction? Actually, let me do that in red. You want me to go the opposite direction of the direction that I already have computed? Okay, well, the opposite direction is just going to give me a minus sign in the output value. We have already computed the counterclockwise line integral to be pi, and so therefore carrying over this minus sign, we get negative pi. That's a lot easier, isn't it? Right? We didn't have to parameterize the curve all over again just so that we could have the parameterization going the right direction. Right? We're just capitalizing on this theorem right here that says, oh, you want to compute a line integral going an inconvenient direction? Hey, no sweat. Go the convenient direction instead. Don't forget your minus sign to fix it. Nice and simple. Really good way to go in a lot of cases. Okay, so that's 3 different methods here. Let me talk about the 4th method. I basically don't endorse the 4th method. It's not exactly wrong, but it is unnecessarily awkward. And again, let me just remind you, the focus here is not on answers. The focus is on good reasoning, right? And reasoning needs to hold water and be, you don't want to make implausible leaps in your reasoning and accept it just because you get the right number at the end, right? That's not good. So the 4th method is to say, look, we've already parameterized it one way. How about we say we're going to use the same parameterization, but we will instead do the integral from pi to 0 of, blah, blah, blah. And the fact that our integral goes from pi to 0, the fact that we're starting where we previously ended and ending where we previously started, and figure that ought to just account, right, for the fact that we're going the wrong way. Well, that will give you the correct result. But I kind of feel like we're invoking the idea that t, which of course we think of as time, right? T is going from pi to 0. T is going backwards. T representing time. I feel like this is kind of invoking time travel, just a little bit, right? Kind of, sort of, maybe a little. I think it's an ugly, ugly thing to include in your argument. Right? Now, to be more precise, yes, we could make this airtight, right? But you would then have to make an argument about which of the components of the integral are the same and which are different and why. And there are some little subtleties in there that I don't think you want to have to be responsible for actually arguing through. So I think this is a really bad argument for that reason. Now, again, it does give you the correct answer, but it gives you the correct answer for a much simpler reason, which is, this accomplishes just inserting a minus sign into the fundamental theorem of calculus. And so, you're just inserting a minus sign, but by way of time travel arguments instead of by the much simpler, we have a theorem that says opposite orientations gives you a minus sign. This we already have worked through the details of. So, much better argument. Please don't invoke time travel. So again, I think that fourth option is suboptimal. Yep.
So just like, let's say we have the bounds for clockwise. The bounds for counterclockwise just do the same thing but flipped.
We literally have this theorem here that says that when you switch the orientation as you describe, right? Switching the orientation,
You switch the bounds.
it'll don't switch the bounds.
Okay.
Right? But that's kind of my whole point, is that if you switch the bounds, is the dx the same or is it different? Is the f the same or is it different? What happens with the dot product? Are these both different, or you got a lot of stuff you got to kind of work out as to what that means, right? And this idea that, just go backwards and everything's just going to work out, I don't think that follows, right? But here we don't have to talk about switching the bounds. Here you can just say, opposite orientation, the answer gets a minus sign. We're done. Our hands are clean. The theorem does the work for us. Yeah. All right. Okay, so on to another question about vector line integrals. And let me just remind you, this is a vector line integral. I don't like that color. I'm going to switch colors here. That's a vector line integral. And recall specifically, we've motivated that from the idea of the vector field itself representing forces. And we've argued that this expression represents work. Okay, so if your vector field represents force, then your vector line integral represents work. Fine. Here's the thing. Vector fields do not always represent forces. Sometimes vector fields represent fluid flows. For example, by telling you the velocity of the fluid flow, there is no force there, right? That's just telling you velocity of the fluid. No force has been mentioned. So in that case, now what does, right? So if we take the assumption that our vector field here is a velocity, looming question then, what's that? What's a vector line integral? It's not work because there's no force. So what is it? Right? Reasonable question. Now, the answer to this question, I'm sorry to say, is a little bit weird. We got a little bit sort of lucky with this first argument. When we argued that this expression tells us work, it happened to be lucky break that this represents a concept that we already had a name for. That was very convenient, right? So the punchline is that in this new scenario where the vector field represents the velocity of a fluid, the answer for what the vector line integral represents doesn't happen to be something we already have a name for. So that's going to make it seem like kind of a weird answer. Ultimately, though, it's a perfectly sensible and reasonable thing. We just have to kind of reason through it. I copied this here just for convenience of reference. There's nothing there that we don't already have written down a few pages back. So nothing to look at there except, again, convenience of reference. Here's how we're going to answer our new question. If we have a curve, we want to talk about a line integral, vector line integral along that curve. What we're going to do, this is going to seem like it comes absolutely out of nowhere. We're going to take a piece of area perpendicular like that, we're going to kind of drag that along the curve to create a, what we call this, I guess, just a thin kind of region, something like that. So long, skinny, it's almost like a tube, but it's not a tube, right? It's not confined inside there. It's just this is just a bunch of fluid that happens to be near the curve. And here's a question we're going to ask, a seemingly weird question, right? It's going to turn out again to connect up with what we're interested in. What is the total over all of that fluid? What is the rate that fluid is flowing along the curve? Now, keep in mind, any little piece of fluid, like if you take, here's a little piece of fluid that's, somewhere along this curve. That one little piece of fluid, well, it's going to be flowing with some velocity. Some of that flow is along the curve. Some of that flow is not along the curve. And again, we're interested in flow along the curve. So we're going to be interested in that component of the velocity, not the velocity itself. And good news, it's easy to write all this stuff down. That little piece of volume, not much to it. That little piece of volume is just the area of the cross-section times ds, representing kind of the length of that little piece of curve. And this component, well, we know how to compute components. Components are dot products with unit vectors. We already have the unit vector in that direction. That's our capital T, right? Reminder. Capital T here is the unit vector pointing in the direction the curve is going. Right. It's easy to write down how much fluid, to what extent is it flowing along the curve, and then we just want to add that up. I'm just going to say all together then, each little piece, if I now add up over the entire curve, and just kind of, multiply this out, stick it in there, kind of move things around a little bit. And we get to our nice punchline. And the punchline, the answer to the question, is this expression right here. Now, before I tell you how useful this is, let me point out one aspect of this answer that I'm going to say is, let's see how to say this, disappointingly obvious. The fact that it depends on the area, well, of course it does. Bigger area would give you more fluid. More fluid means more fluid flowing along the curve, right? I mean, that kind of seems easy to see it coming. And ultimately not really what we're interested in. This cross-sectional area here, that area that figures into our answer like that, it could be anything. It's not really actually particularly relevant to the curve at all. In fact, the only reason I put this in here is so we can have actual volume of fluid to talk about in the first place. Right? So I'm going to say that the fact that there is a cross-sectional area in the answer is just not that interesting. And so I want to factor that out. I want to make that... I want to get that out of the statement of the question. And so I'm going to say we're going to basically rephrase the question to per unit area, what is the rate that the fluid flows along the curve? And that makes that factor of A kind of sort of disappear from the calculation. So the nice punchline then is the integral that we're ultimately interested in. Keep in mind, what we're trying to figure out is what does this integral represent? And what it represents is how much the fluid's flowing along the curve per unit area. So if you're willing to sort of accept that, well, yeah, of course it's proportional to the area, that part's clear, then a simpler, streamlined way of saying this is that the vector line integral represents in some sense, in some appropriate units, the extent to which the fluid is flowing along the curve. And again, we don't have a pre-existing name for it, so this is, we don't get that sort of feeling of satisfaction of, oh yeah, that's volume, right? There's something nice and cathartic about those one-word answers. That's what it is, right? We just don't have the word for it, but this is what it represents. Okay. All right. Now, there's a particular application of this. Turns out to be really important. We're gonna see one little small application of this right here, right now, in just a couple of minutes. But the big applications, the really cool stuff we're going to see about this special case right here will come later, probably Friday. Factors into a really powerful, really important idea. But that's getting ahead of things. Let's consider the special case where we're talking about a closed curve. All that means, a closed curve is just a curve that starts and ends at the same point. Okay, so it kind of loops back around on itself. Okay, so if your curve here is a closed curve, in that case we give a name to the vector line integral. The word we use for the vector line integral is circulation. And we use this symbol. This is the lowercase Greek letter sigma, which I have to assume is sigma for circulation. Seems like an easy choice. Turns out to be a really interesting thing. Let's talk, though, about, what can we, geometrically, how would we visualize this idea of circulation? So here we go, looking at our expression. Let's see here. We've got a fluid here, by the way. And let's start with this first picture, this first case. Got a fluid kind of flowing along like this. And let's see here, that fluid, it would seem we're going to be dotting that with our dx vectors. Now, keep in mind, dx vectors represent displacements along the curve. Like that. And now let's look at the integral itself. What are the contributions, anyway, to this integral? The sort of piece-by-piece contributions to this integral are the dot products of your vector field with your position differentials, your displacement vectors. Right? And these dot products, I'm going to just make a geometric appeal, all those vectors are pointing in the same direction, so those dot products are positive. Right? You expect all positive contributions then, and then, in fact, in this case, the circulation as a whole is positive. So let's think about how we could say this. Now, again, we've already talked about the fact that this expression, this vector line integral, represents the extent to which the fluid flows along the curve. So the fluid, you can literally see here the fluid flowing literally, very much so along the curve, right? The curve goes around in a circle, and that happens coincidentally to be kind of an actual circle here, but it doesn't have to be. If you think about the tangent vector, the unit tangent vector that starts straight up there, as you go around that curve, that unit tangent vector literally goes around exactly in a circle. So let me connect the dots here. If the fluid is flowing along the curve, and if the curve is going around in a circle, it's like this is a measurement of how much the fluid is representing a flow that goes around in circles, kind of, sort of, if you will, somewhat. Everybody see the little connect the dots there? So that's going to be our big interpretation. That's why we have the term circulation here. It's literally a measurement of the extent to which the fluid represents a rotation happening in the fluid. And I think a nice way to think about this is, that we'll recall from Chapter 3. And in Chapter 3, we talked about having a solid... I like the idea of a leaf kind of floating in the water, right? The water that is, whatever this vector field represents the flow of. And the idea is that if the fluid is doing like this, then that'll represent a rotation of the object. All right, so this is a really nice interpretation of the idea of circulation. Circulation is a measurement, in some sense, of how much you would expect little floating leaves to be rotating as a result of the fluid. Everybody buy it? I do want to warn you about one thing. I made this clarification back in chapter 3, way back when. There is a temptation to think of this as being a measurement of flow lines. And now the way I have the vector field drawn here, if you were to, just kind of follow the vector field and see what curve do you trace out, yes, in that case, this would give you a circle. This is a coincidence. Circulation is not about flow lines. In this case, it just coincidentally happens to be that the rotation of the fluid coincides with there being a flow line that also is a circle. Doesn't have to be, right? And recall back in chapter 3, I showed you an example of a vector field where all the flow lines were straight lines. But nevertheless, there was still kind of a rotation, an overall rotation in the fluid. So please don't be distracted by the idea of flow lines. That's just not what circulation is. Okay. All right, a couple more examples real quick. Let's see here. Now, same fluid. Literally the same fluid as I have on the left. But here I'm going to look at a different curve that goes the other way. This curve goes clockwise instead of counterclockwise. And there is a temptation to say, well, look, it's the same fluid. If it's the same fluid, we're going to have the same circulation, aren't we? Because, come on, it's the same fluid. And this is not true. You got to keep in mind, circulation, oops, wrong color. Circulation is an integral that, yes, it does depend on the fluid, but it also depends on the curve, right? And you might think of this as that circulation is kind of a comparison between how the fluid is rotating and how the curve, as you go around the curve, your position is kind of sort of rotating in a sense. So if we were to play this same game of dot products, dot products with the dx vector as we go this direction along this curve, notice that these contributions to the integral, right, these dot products, blue dot green, well, these vectors are all going opposite directions of each other. These dot products are all negative. This circulation would come up as negative, not positive. And one way to think about this, the way I like to think about this, is think of the direction that the curve is going as part of the question you're asking. When you ask, how is this fluid circulating, specifically think of it as, to what extent is the fluid circulating clockwise? All right, we're going to use this curve. That curve is going clockwise. This integral, therefore, is measuring the extent to which f is going clockwise. And the answer is, to what extent is this vector field going clockwise? Well, a negative extent, because it's going counterclockwise. So, again, kind of makes sense. Suitably interpreted. So, something to keep in mind. Last example real quick is just to point out that these first two examples are, tailor-made to be as sort of bluntly obvious as possible. The vector field is either exactly along or exactly opposite of the curve, but that won't always be the case. And so, for example, if we think about this curve here, again counterclockwise, but kind of offset to the right now, that curve, well, awkwardly, the same fluid is sometimes going opposite the direction the curve is, but elsewhere is going in the same direction that the curve is. So these contributions in this case are sometimes negative and sometimes positive. So at an eyeball glance, in this case, it's really not at all obvious whether this circulation is positive or negative. And this one we'd have to crank out or understand by some other means. And by the way, we are going to have a fantastic other means coming up again probably on Friday. Okay, yeah?
Algebraically, how would the direction of what the curve, where the curve is going, be defined? Here it's drawn
by a formula.
Okay.
So vector fields you got to keep in mind. I mean, I'm just writing them by name here and drawing pictures, but the way we describe vector fields is with an explicit formula.
Now it's drawn out, so if it wasn't drawn out,
Yeah. You plug and chug actual algebra. Yep.
Okay.
Yep. Just like in the previous examples we did on Monday.
Okay.
Yeah. All righty. Okay, a couple of really nice special cases for y'all to be aware of. Sometimes you get lucky. This example is totally awesome. This is in the spirit of a bunch of cool calculations that I saved myself a lot of trouble with when I was an undergrad. And again, most of y'all being engineers, y'all have the opportunity to save yourselves loads of trouble as well. Anyway, here we go. The theme of this is keep your eyes open for geometric good fortune. It happens, and it's awesome. So we'll start off with the curve. We've got a curve C, and I'm giving you a spherical parameterization here. That's weird, right? I've never given a spherical parameterization before. If you're going to do anything with a parameterization, compute derivatives and stuff like that, it's got to be in rectangular form. So we are going to have to take this rho, phi, and theta and plug it into the usual conversion formulas, and it's going to get super ugly really fast. This is an algebraic nightmare of a curve. Right? Anybody see that? Like this weird curve along here like that, whatever that is. Now let's think about the vector field. Here's my formula for my vector field. That's not so bad. Anyway, the point is we have a vector field, we have a curve. The reasonable question is to compute the vector line integral. How would I do that? Well, I guess I got to write it all out in the algebra, and gosh, it's going to be just such a nightmare, right? We really don't want to have to do that. Total nightmare. So here's where geometry is awesome. Let's look at our curve. And it kind of leaps off the page that rho equals 1, which means we are entirely confined to the unit sphere. And now I'm going to make a geometric appeal. If you are moving on the unit sphere, then your tangent vectors are all parallel to that same surface, parallel to that same sphere. So all of our dx vectors here, those dx vectors are all tangent to the sphere. Is that cool? All right, here's the next appeal. Look at our vector field. Our vector field is a scalar multiple of the position vector. Now, again, the vector field is what we're actually interested in, but being as it is a scalar multiple of the position vector, it's also parallel to the position vector. And wait a second, the position vector there, let me get rid of what we don't care about anymore. That position vector, if you think about it, is a radius of the sphere. Another geometric appeal, spheres have a fantastic symmetry that all radii are perpendicular to the sphere. So this is perpendicular to the sphere. And therefore, by the way, so is the vector field itself, also perpendicular to the sphere. So our vector field, perpendicular to the sphere. Okay, well, it's all over but the shouting. These dot products that contribute to the vector line integral we're interested in, they're a dot product of something perpendicular to and something parallel to the sphere, that means these two things are perpendicular to each other. That means their dot product is 0. We're adding up a bunch of zeros, and that adds up to 0. Game over, we win. No horrifying spherical coordinate conversions and nasty integrals involving trigs and exponentials and possibly worse, right? Just clever geometry argument, and the whole thing falls out. It's pretty cool, isn't it? So be on the lookout for this. Now, I've already told y'all my absolute number one favorite time-saving computational hammer, right? And that is symmetry arguments. And I made a bazillion symmetry arguments when I was an undergrad. I think y'all will too. Be on the lookout for symmetry arguments, of course, right? But also, I mean, I don't know. I don't know if I'd say a close second, but a perfectly respectable second place runner-up is awesome geometry coincidences like this. This comes up. This is not manufactured nonsense that you'll never see in the real world. This is very representative of, I don't know, maybe 10% of the integrals that I saw as an undergrad taking physics classes. That's still a lot of integrals, and again, heads up, it'll save you a lot of time. Did I see a hand? Yeah. Mm-hmm.
Can you just explain again how the dx is parallel to the...
Well, yeah, it's just the observation that if you're moving within a surface, right? So, I mean, let's take the table here as an example. If I'm moving in the surface of the tabletop, all my tangent vectors, all my velocity vectors have to be tangent to that surface.
Oh, okay.
That's all it is. Yeah. Okay. All right. So again, heads up. And by the way, it's not always going to be a sphere. Sometimes it's a plane. Planes have a different kind of awesome geometric convenience. Spheres have a different awesome geometric convenience. There's probably some other examples that aren't coming to mind at the moment. But always be open-minded to the possibility. Okay, this next thing is notation, mostly just a point of notation, and a little bit of a cultural point I'll make. But there's arguably nothing really new here. We established that back in Chapter 3. We take derivatives one coordinate at a time. I can write that out. You can distribute the dt. That's not that weird. And then, looking at these expressions, like this right here, what do you think we ought to call x prime dt? Well, how about dx? I mean, what else would it be? Right? So, altogether, you basically expanding by coordinates, we have here an alternative notation for our dx vector. That's just notation. I didn't really do anything. Right? All right, well, here's the thing. If your dx vector, you write out in coordinates. And if your vector field, of course, your vector field is going to come to you probably written in terms of coordinates, or you can write it in terms of coordinates in most cases. Then notice this dot product itself. The dot product itself, you can just dot it out in coordinates like this. Everybody see how that comes together there? Just kind of playing around with notation. Again, I feel like I didn't really do anything there, right? So anyway, here's the nice, well, that's the wrong word. Here is a punchline. An alternative notation to represent vector line integrals is that. And some people really like this notation. So instead of writing integral f dot dx, some people prefer to write integral p dx plus q dy plus r dz. Now, I got to tell you, I don't think I'm making a good sales pitch for this notation right now, right? I mean, look, it's clearly bulkier, right? Why would anyone want to write out a bulkier notation to represent what is, in fact, exactly the same thing? Well, I don't have an answer. I don't think you're going to want to use this notation most of the time. The main reason I'm showing you this notation is because other people like this notation. Now, what I do want you to understand is why they like this notation. This notation is pretty much what integrals of differential forms look like. And I haven't told you what differential forms are. In case you're curious, they are discussed kind of briefly in Chapter 8. There's a lot to say about differential forms. Anyway, if you do write things in terms of differential forms, this ends up being pretty much what it looks like. Not exactly, but really close. It's pretty much this. Okay? And so, okay, whatever. Who cares about differential forms? Oh, well, differential forms are super powerful. Differential forms are a tool that allow you to answer questions that stumped the mathematical community for 100 years. They are crazy powerful, very important. The only thing is, they're super useful and super powerful in contexts that are well beyond Math219. Right? So arguably the point here is that this notation is really great in ways that you'll never have a use for. Right? So again, you're not going to personally get anything out of this notation. But because there are other uses for it, that notation is in common use. Even in situations where they're not using the power of it. Some people still like to write their vector line integrals like this. So how does this affect you? And the punchline is you're going to see this notation outside of Math219. Right? Even within Math219 to some extent, because the book takes the same position I think that I do, which is that, they kind of have to mention it because you're going to see it in your future in engineering courses, physics courses, etc. Right? So I want you all to be aware of this notation. I want you to make the realization that when you see it, when you see this notation, realize the following three things. They're talking about a vector line integral. All this business about dx, dy, dz is just kind of a fancy way of representing the dx vector. And these seemingly disconnected integrands are the coordinates for the vector field f that they're doing a vector line integral of. So you can take anything written in a form like this and kind of reverse engineer in possibly a what you might call a preferred notation what the vector line integral is that they're talking about. And that's what I do. Is that cool? I mean, is everybody okay with that? No. Anyway, there you go. Okay, moving along. Symmetry theorems, really good stuff. We've talked about symmetry theorems, specifically the odd symmetry theorem for single variable integrals, double integrals, triple integrals. And here's another one. You're going to notice that the way that's written down is laid out on the page deliberately, exactly, almost like I'm copying. In fact, I think I literally copy-pasted, right? And then edited appropriately, just, micro edits. But this is morally identical to the other symmetry theorems that we talked about earlier. With all the same deal, right? You need the integrand to be odd. You need the domain to be symmetric. The scalar line integral is 0. Don't forget both conditions have to hold. Don't forget it's got to be the same line for both symmetries. And yeah, it really works the same way as all of our other our odd symmetry theorems that we wrote down. Have fun. I'm a big fan. It's super useful and convenient. So, absolutely. Here's the bad news. This is only for scalar line integrals. Strictly only for scalar line integrals. There is no odd symmetry theorem for vector line integrals. It just doesn't work. And, if you want to know why, in some sense what goes wrong, roughly speaking, what goes wrong is that if you look at your symmetric domain, and again, work with me on the, my shortcomings of artistic competence. And if you imagine a curve, that is symmetric, let's say over a line like that, And if you start thinking about, well, this little piece and that little piece, they contribute to the Riemann sum, and do they cancel or do they not cancel? Well, think about what your tangent vectors look like. Your tangent vectors look like that and this. They're just not the same. The DS's are the same, right? The size of this is the same as the size of that. Yeah, sure, those are the same. Tangent vectors, not the same. They're also not negatives of each other. We're out of business. We can't compare these. There is no cancellation to talk about. We lose. So the theorem just doesn't work. So please do be very careful about this. It is very easy to look at this statement here, to over-interpret, the devil's in the details, and this is one of them, and forget that it's got to be a scalar line integral. So I'm making a big deal out of this to try to cut down on the number of misuses. You cannot use it for vector line integrals. It doesn't. There is no such theorem. And it's absolute nonsense. Okay. All right. Okay, so moving along. So we're into section 6.2 now. 6.2 is a first step into a substantial conversation where we're going to have over the next, most of the rest of the course. There's a bunch of theorems called vector calculus theorems that we're going to be presenting. And they were discovered historically at different times in different ways. And very quickly after people started writing down these theorems, again, by different people in different contexts, different times, eventually people started to notice, wow, these theorems really look like they have a lot in common with each other. Well, that's weird. Can we generalize? Can we view all of these theorems as being kind of the same theorem? Are they all special cases of a single, larger, generalized theorem? And this is something that they hunted for a long time, something on the order of 100 years. Mathematicians were trying to figure out how these theorems are clearly connected to each other. What is the connection? What unifies them together? And by the way, the thing that made it possible to unify them is differential forms. Just, that's a, FYI, right? And that's why one of the reasons differential forms are cool. So we're about to talk about all these theorems, and I can't tell you, because it would be way beyond the scope of this class, the connection that got realized, which, by the way, I think happened in the 1930s or 1940s, somewhere along there. This is very modern math, right? Newton didn't know the first thing about this stuff, right? Very recent, very modern. As I like to say it, I know people who knew the guy that figured this out, right? That's how recent it was. So anyway, I can't tell you the full story. It's too much. But what I can do is take the spirit of what they all have in common, ultimately deep down, and just kind of present all the theorems from sort of the same point of view. And I think that does a lot of the benefit of showing you the connection without showing you all the scary, deep, sophisticated, abstract, intimidating stuff that is the true full story. So in order to do that, I have to develop some concepts. The next 2 pages of notes is general discussion, setting up kind of a point of view and a framework. Arguably the next 3 pages of notes, depending on how you count. General points that will apply to a bunch of different theorems. So please be patient with me on this. It is going to seem a little tedious. It is going to seem like, what are we doing here? Where are we going with this? This seems pointless. I know it does seem that way, but it's really not. This is actually a really powerful set of ideas. Okay, so that said, here we go. This first one is not a deep point at all. I'm going to define what I mean by a quantity on areas. And it just says that if you give me an area, something like that, you give me an area, then I can define a corresponding quantity. So for example, if you give me an area, I can say, okay, well, how much mass is in that region of area? That's all. I mean, it's like it's just a quantity of interest. You give me a region, there is a corresponding amount of whatever that quantity is. So mass is a nice example. Area itself is a quantity, because if you give me a region, we can talk about the area of that region. Here's a silly one, arguably, perimeter. That is a quantity defined on regions. If you give me a region, I can talk about the perimeter, like that. How far does it take? Do you have to walk around that region? Okay. And I'll just make a couple of innocent observations here. They may or may not be physical. Right? Mass is physical, but perimeter is really more geometric, I think you'd say. Okay. All right. Now here is a special kind of quantity. And I've referred to these indirectly in Chapter 5, talking about integrals. I talk about accumulating quantities, and my favorite, y'all will recall, is mass. I talk about how mass has this feature that the whole is the sum of the parts. Right? If you have some whole region like this here, okay, we've got this lump on the here in gray. You ask, let's talk about the mass that's within that region. Well, one way I could tell you how much mass there is I can tell you how much mass there is on R1, and then how much mass there is on R2, and, well, of course, the total mass is the sum of the masses and the pieces. Well, of course it is. That's how mass works. Right? So this is an accumulating quantity. This is what we mean by an accumulating quantity. The whole is the sum of the parts, and literally the mass of the whole is the sum of the mass of the left part plus the mass of the right part. So the sum of the parts. Everybody see what I mean by that? Every integral we've ever computed has been in relation to a quantity that has this feature. And it seems like a silly thing to observe because, isn't that obvious? Isn't the whole always this? What else would it be? Isn't that what whole means? Right? When would the whole not be the sum of the parts? Okay, here's a pretty good counterexample. Perimeter, previously discussed, perimeter is not an accumulating quantity. The perimeter of the whole is not the sum of the perimeters of the parts. You just look at the picture. Right? So, the perimeter of the whole is that distance. The perimeter of the left side is kind of overlaps a lot with it, but then there's that piece in the middle. The perimeter of the right side is, well, again, it kind of overlaps quite a bit with the orange, but then there's that part in the middle. And green plus blue is more than orange here. Does everybody see that? Okay, so this feature of being an accumulating quantity is not to be assumed, it's not to be taken for granted. It is a special property that some quantities have. And it's totally awesome when it does, but some quantities have it and some quantities don't. Is that cool? Everybody see the distinction? Alrighty. By the way, just a little fine point. Specifically, when I say accumulating quantity, you'll notice that I've specified here, these are quantities that accumulate over areas. And what I mean by over areas is that it's the area. It's the area, specifically, that I'm going to cut up into pieces. I'm going to cut that. I'm cutting up the area, and I'm looking at the quantity on the left piece of area, the right piece of area, and the whole union of area. And that is the context in which I want to ask if the whole is the sum of the parts. So some students get confused and think, oh, well, yeah, but if you chopped up the perimeter itself, wouldn't that actually add up correctly? Yes, it would if that were what I was talking about, right? But we're chopping up areas. We're not chopping up perimeters. Perimeter is the quantity. We're interested in whether it accumulates over areas. You don't want to mix those up. Does that make sense? Does everybody see the distinction I'm talking about? Okay. Yeah.
Just what we're saying is that perimeter would not accumulate over.
Correct.
Okay.
That's right. Yeah, exactly. Yeah. Right here. Yeah, it does not accumulate. Yeah. Okay. So why would I care about accumulating quantities aside from the fact that integrals work? Oh, I'm sorry. I am out of time. So okay, we will draw the line right here, and I'll tell you why we care about accumulating quantities on Friday. See y'all later. Don't forget about attendance if I didn't already get you.